Hey, what's up everyone? This is the Physics for Engineering, and today we keep talking about the wheel, how the wheel works. This is the second part of the video, and before we continue, I highly recommend to watch the first part of the video. Nevertheless, let us have a look what was the outcome of the first part of the video, where we have derived the following. If we have a wheel mounted on the X, and this wheel has the following geometrical parameters like an outer diameter of r and inner diameter of r small, and we have a friction between the shaft and the wheel mu, then our force required to move the wagon is defined by this equation. If we now do the following approximation, that mu square approaches to 0, which corresponds to the real conditions, because our mu typically is low value, therefore the mu square will be very close to the 0, then we come up to the following simple equations, which is easy to remember, that our driving force is proportional to the gravity times the friction coefficient and times the ratio between the shaft radius and the wheel radius. We have also defined what is the main function of the wheel, so why the wheel works, why the rolling resistance is much lower compared to the friction between the shaft and the wheel. This basically comes from the system equilibrium requirement. If you write the equation of the torques acting on the wheels around the center of rotation, then we come up to the following, that the torque of the sliding force F friction, which is equal to the radius of the shaft times the friction force, must be equal to the torque of the stiction force, which is equal to the wheel radius times the stiction force. Considering the fact that our driving force is equal to the stiction force with different sign, we come to the following equation, that our driving force is equal to the friction force times the ratio between the shaft radius and wheel radius. That gives us the understanding why actually wheel reduces the friction between the shaft and the wheel itself. This is because the lever arm ratio of the sliding force and the stiction force. The smaller this ratio, and the smaller the force required to move the wheel. We did also comparison for different types of the vehicle on the first video, where we used real numbers. So I highly recommend you to watch the first video and have a look on the results. Today we continue discussion about the wheel, and in this video we will do the following. As you remember, we did not consider the rolling resistance during our first investigation, because we wanted to focus on the understanding how the driving force depends on the wheel geometry and also the friction between the shaft and the wheel. But today we will include the rolling resistance in our investigation, and therefore the outcome would be already the total rolling resistance of the wheel, including the friction between the shaft and X, and also including the rolling resistance of the wheel, which is coming from the rough rod, like on the picture, and the rod deformation, or from the wheel deformation in the contact point between the wheel and rod if we have a rubber wheel, for example. The rolling resistance in this case is defined as following. Then the normal force between the rod and wheel is tilted as on the picture, and the rolling resistance coefficient CRR is defined as following. This is the B divided by the radius of the wheel, where the B is the rolling resistance coefficient, which has units of measure of length, or CRR, which is dimensionless rolling resistance coefficient. So let us now to solve this task and define what would be then the driving force required to move the wheel, having the friction between the shaft and wheel, and also the rolling resistance between the wheel and the rod. In order to solve this problem, we need to define the forces on the picture. First of all, we will define the forces acting on the shaft. This will be the gravity force, this will be the driving force required to move the vehicle, this will be the reaction force between the shaft and wheel, and this will be the friction force. Let us now define the coordinate system and write the condition for the system equilibrium. This will be the result of all forces acting on the X is equal to 0, because we consider that our wagon will move without acceleration with the constant force. Then we do the projection of all the forces on the X and Y axis, and in the end we come to the following equation, which has a relation between driving force and gravity force. As a second step, we will define the forces acting on the wheel. This will be the reaction force between the wheel and ground, wheel and rod, this N. This will be the reaction force between the shaft and the wheel, F reaction. This will be the friction force, and this will be the stiction force between the wheel and the rod. Then we move our coordinate system to the contact point between the wheel and ground and write the condition for the system equilibrium for the wheel, as the result of all torques acting on the wheel around this point is equal to 0. With consideration of definition for the friction force, we come up to the following equation. So as a result, we have system of two equations. This is the full system of equations because it has two variables and two equations. So first variable is the driving force, Fd, and second variable is the alpha. This is the tilting angle of the reaction force between the shaft and the wheel. So we can now solve this system of equations. If you look now to the second equation, then we see that this equation has only one variable, which is alpha. This means that we can already derive the alpha from this equation. This otherwise isn't the easy process. Nevertheless, after some calculation, we can derive the following, that the sine of this angle is equal to the following equation. We can now take sine of the alpha and put it to the equation of the driving force. We still need the cosine of the alpha, therefore we can derive it from the second equation, and also put it to the first equation. And then as a result we come to the final equation of the final complete rolling resistance of the wheel. This is the ratio between the driving force and the gravity. It will be function of all these parameters, which is the geometry of the wheel, the friction coefficient between the shaft and the wheel, and the rolling resistance between the wheel and the rod. At first look, this equation is really big and complicated. But let us check some boundary conditions for these equations. For example, we know if the friction coefficient between the shaft and wheel is 0 or close to 0, then the outcome of the equation should be just the rolling resistance coefficient. And this is the case. If you now pause the video and check this equation with mu equal to 0, then we will have just a rolling resistance friction coefficient. This corresponds to our expectations. And the second boundary would be the opposite, that if our rolling resistance coefficient is equal to 0 or approaches to 0, then we must have the equation which we defined in our first video. So this is the rolling resistance coming from the friction between the wheel and the shaft. If you now pause the video and put CRR equal to 0 in the big equation, then you will come to this equation, which is also our expectation. This basically means that this big equation describes the complete rolling resistance of the wheel, including the friction between the shaft and wheel, as well as the rolling resistance between the wheel and the rod. But this is something what is really difficult to remember. Let us do some simplification of this equation, the same way as we did it at the first video. So let us approach the mu square to 0, considering that our mu, our friction coefficient, is small value. And additionally to that, we can approach the product of mu and the rolling resistance also to 0, because the mu is small value and the rolling resistance, this small value, is well. So we have mu square approaches to 0 and mu times CRR approaches to 0. And considering these approximations, we come to the following equation, which is much simple and easy to remember. So this means for the condition when our friction between the shaft and wheel is small value and also our rolling resistance is small value, then our complete resistance to the motion is the result of the rolling resistance coefficient coming from the friction between the axle and wheel plus the rolling resistance coming from the rod or wheel deformation in the contact between the wheel and the rod. Therefore, if we want to make the exact calculation of our rolling resistance, we can use, of course, our complete complex formula. But if we want to do approximation for the smaller friction coefficient and also smaller rolling resistance, we can definitely use this simple formula, which is also very easy to remember. So let us summarize what we have. So the outcome of this video is the following. If we have a wheel which has a geometry of R capital as the outer radius and R small as the inner radius in the contact between shaft and wheel, if we have a friction, if we have a sliding friction between the shaft and the wheel, and we have also the rolling resistance coefficient, which is CRR between the wheel and rod, then our complete rolling resistance of the wheel can be defined by the following formula. This is the result of the rolling resistance coming from the friction between the shaft and wheel, and the rolling resistance coming from the contact between the wheel and the rod. So this equation can be used not only for the wheel, but also for any roller or any rolling mechanism included in our system. With this note, I would like to end this video. Thanks for watching, I hope you like it, so please hit the likes, subscribe, and see you next time.